Okay, everybody, welcome back. Today we want to review something I mentioned last time, and that was this hydrogenation reaction where you basically add one molecule of hydrogen to a pi bond to create two new CH sigma bonds. And I told you that was, you can call it a hydrogenation reaction. That's how we hydrogenate vegetable oils to get rid of the double bonds that are reactive so that the oil will have a longer shelf life. But I told you this reaction was an example of a kind of reaction called a reduction. Did I press record? Yeah. A reduction reaction. And in organic chemistry, you can define reduction of an organic molecule as an increase in the number of CH bonds or a decrease in the number of bonds between carbon and an electronegative heteroatom. This is a little bit different from how you may have defined reduction in general chemistry. In general chemistry, reduction means adding electrons to things. That's still true in organic chemistry, but the way that manifests itself is through an increase in the number of carbon-hydrogen bonds or a decrease in the number of bonds between carbon and an electronegative heteroatom. So for example, well, let's just restate that here. Increase in number of CH bonds, or two, a decrease in the number of CZ bonds, where Z is an electronegative heteroatom, like carbon, like nitrogen, or oxygen, or halides. The opposite of reduction is oxidation. And so oxidation will involve a decrease in the number of carbon-hydrogen bonds. Oxidation may also, and these are sort of and or, either one of these is evidence for oxidation/reduction. Another way you can see oxidation is an increase in the number of carbon heteroatom bonds between carbon and an electronegative heteroatom. So, in the example that I showed you from last time, the hydrogenation of oils, you can see that the alkene, carbons 9 and 10, each only have one CH bond. We reduce the alkene to the alkane, and now they each have two CH bonds. So that's how you can recognize something that's reduced. Okay? So your quiz has some examples of how to do this. The first question on your quiz asks you to rank the molecules that I've shown you in order of, let's see, increase from least oxidized to most oxidized. Another way to say least oxidized would be most reduced to least reduced. So remember, you're looking for either, for reduction, you're looking for an increase in the number of CH bonds or a decrease in the number of CZ bonds. For oxidation, you're looking for a decrease in the number of CH bonds and an increase in the number of CO bonds or CZ bonds. Okay, so start out with A, see if you can figure A out. Take just a minute to compare those things. They are three different hydrocarbons. They have the same number of carbons, but you can see one is an alkene, one is an alkane, and one is an alkyne. And if you need to, you can fill in the CH bonds that are implied but not shown. Okay, have you got an idea yet? You got something down on paper? If so, feel free to consult with a friend and or a person and or a new friend, a person sitting next to you. All right, have you come to something of a consensus? Okay, what do you got? What is the most reduced or least oxidized hydrocarbon up there? Is it the alkane, the alkene, or the alkyne? Alkane is the least oxidized, most reduced. Okay, how can you tell that? What's the explanation? Yeah, it's got the most CH bonds. I mean, the one thing you can do is sort of dismiss the methyl groups because they're the same in all three molecules. The only difference is in the two carbons in the middle. So alkane would be most reduced or least oxidized. Then what? Then alkene, and then alkyne, which is going to be most oxidized, least reduced. Okay, what potential pitfalls or sources of confusion did you detect there? Anything that was concerning that we should talk about? Go ahead.
Wait, so with that one, is it just a triple bond and there's two carbons on?
Yeah. Yeah, you maybe haven't seen how we draw triple bonds in skeletal structures before, so that's new. This drawing is fully equivalent to this one. In other words, in skeletal structures of alkynes, there's not going to be a bend there, so you sort of have to detect the alkyne by the presence of the two pi bonds. And then on either side of those pi bonds, you've got carbons. The reason the alkyne is drawn that way is because those carbons are actually sp hybridized. They are linear in shape. We're not going to encounter alkynes a lot in biology, so we spent no time on that at all. And then I forgot that it would look unfamiliar to you, so thank you for pointing that out. Other questions about how the alkyne looks and how to interpret that? Go ahead, you had something?
I have a different question.
Sure.
So I understood how to rank them, but I'm just wondering what's the definition of oxidized?
Reduce means in organic molecules, a reduced molecule will have more CH bonds than an oxidized molecule and or fewer CZ bonds. So reduction is an increase in the number of CH bonds or a decrease in the number of CZ bonds. Oxidation, oxidation is an increase, there we go. Oxidation is a decrease in the number of CH bonds or an increase in the number of CZ bonds. All right. So with that in mind, why don't you try B now? This one you can come up with an answer either by paying attention to CZ bonds or by paying attention to CH bonds, and you should get the same answer. So look at the differences. And you know what? We actually, yeah, I suppose. That's fine. We'll just leave it as it is. Okay, so what have you got for B? What is the most reduced molecule for B? Second one, this is ethane, the 2-carbon purely hydrocarbon. Okay, so we'll start that, we'll call that number 1, least oxidized. Who's next? The alcohol. How do you know that? How did you know it's oxidized relative to number 1? 1 new carbon-oxygen bond. Good. That's a form of oxidation. And if you wanted to, you'd see there's 1 fewer CH bond. How about next? What's after the alcohol? Aldehyde, 2 bonds to oxygen and 1 fewer CH bond relative to the alcohol. Then who? Yep, good. Okay. Now, I put CO2 on the list, and then I just realized that CO2 is kind of weird because all of these have 2 carbons each, and then CO2 only has 1, so it's maybe not a fair comparison. So I just quickly wrote over here some other 1 carbon molecules, and you'll see hydrocarbon, alcohol, aldehyde, acid, and then there's 1 more oxidation state possible, and that's to CO2. Do you see how CO2 is oxidized relative to this carboxylic acid? 1 fewer CH bond, 1 more CO bond. Okay. And so this is important because your body actually takes a polyalcohol / aldehyde called glucose and systematically oxidizes it into 6 molecules of CO2. And you can do that without having a metabolic system. You can just light sugar on fire and it'll burn and become CO2. But of course, that's not a controlled way to do it. You won't get a lot of usable energy out of that. But it's important for you to realize that what your body is doing when it's metabolizing things is trying to oxidize things from alcohols to aldehydes to carboxylic acids to CO2. Okay? All right. Any other issues we need to talk about there? Oh, yeah, go ahead.
So if we were asked to like maybe oxidize a molecule, would we just add like another, like a double bond to the oxygen or something? I don't know.
So if this were an organic chemistry class that you were going to spend 2 semesters learning OChem, we would totally teach you how to oxidize alcohols to aldehydes or ketones. We are going to learn how to do that, but we're going to learn how biology does it. Yep. There are reagents that do this, and it's kind of fun, and we could talk about it, but I probably will keep the focus on how biology does it. That's coming, if not next week, then the week after that. Okay. One more thing I guess I could add. You can convert alkynes to alkenes with a hydrogenation reaction. How many molecules of hydrogen would I need to do that reduction? Remember, hydrogen's just H2, or if you want to draw the Lewis structure. So how many molecules of H2 do I need to go from the alkyne to the alkene? Just one, right? Similarly, how many molecules of H2 do I need to go from the alkene to the alkane? Yep. So for each double bond, each pi bond that you reduce in a hydrogenation reaction, you're going to consume one molecule of H2O. Sorry, say that again. For each for each pi bond that you reduce in a hydrogenation reaction, you consume one molecule of hydrogen, H2. Okay? So to go from the alkyne to the alkane, you'd need two, right? Yeah?
For the second set from the method, so I just want to make sure, because technically they have the exact same amount of hydrogen.
Yes.
The reason why alcohol is more oxidized than carbon is because of
Well, if you pay attention, it's true that the molecular formula is still C2H6O, and over here it's just C2H6. But you'll see there's one more carbon oxygen sigma bond and one fewer carbon hydrogen sigma bond. There is one new oxygen hydrogen sigma bond. But in terms of oxidation reduction, we're only paying attention to CH bonds and then CZ bonds, where Z is an electronegative heteroatom. Okay, good. Others? All right, so last time we talked about fatty acids and triglycerides, and we talked about how some were solids. Go ahead.
I actually have a question about that.
That's-
I was looking at the problem set, and I understand that saturated fats have a higher melting point.
Yeah.
So we were trying to think through it molecularly, and we kind of came to the conclusion that wouldn't we didn't understand why the saturated would have a higher melting point.
Yeah.
We thought you'd need more energy to break the double bonds.
Okay. Yeah, so let's talk about that because, we really did delve into this last time. You saw a few trends. For example, you saw that the saturated fats in general have a higher melting point, whereas the unsaturated fatty acids have lower melting points. The presence of a single cis double bond in a fatty acid is enough to drop the melting point by more than 60 degrees. So it's a pretty dramatic effect. Now, I'm really glad you were thinking about that. It sounds like the way you were imagining it is thinking about sort of hypothesizing that melting was involving a rearrangement in the covalent bonds. You were trying to rationalize, well, do I need more energy to break a pi bond? It turns out melting is a physical process, not a chemical process. So in melting or evaporating, the molecule itself doesn't change, but what does change is the kinetic energy that that molecule has. And turning up the temperature on something is the exact same thing as giving the molecules in that substance more kinetic energy so that they can move faster relative to each other. So when we're talking about properties like melting point, we're no longer going to talk about how stable the covalent bonds are. Instead, we're going to talk about how strong the interactions between molecules are. And those interactions are weaker than covalent bonds, but strong enough to influence the world that we live in. And so that's going to be our subject today, non-covalent interactions, the ways that molecules can interact with each other without forming covalent bonds. And these types of interactions are going to be weak relative to a covalent bond, but they're going to be strong enough to influence the world that we live in. As an example, the molecule HCl, well, do I want to do this? Yeah, sure, why not? So we're going to come back to triglyceride and fatty acid melting point. But to introduce the idea of non-covalent interactions, compare methane which is a gas at room temperature, and water, which, as you know, is a liquid at room temperature. They're similar in size. In fact, methane has more atoms, and they're all from the second row of the periodic table, at least carbon and oxygen are. But that's a pretty dramatic difference, gas versus a liquid, right? So what makes that happen? Something that's a liquid at room temperature versus something that's a gas at room temperature, the thing that's a liquid must have stronger, what I will call intermolecular interactions. That is, one water molecule must interact strongly with its neighboring molecules than is the case for methane. So intermolecular, that means between molecules. Interactions between molecules in water are stronger for water than the interactions between molecules in methane. So we'd say methane has weaker intermolecular interactions. So to understand that, we need to define what these interactions even are. Okay? Covalent bonds come from sharing of electrons between two atoms. Non-covalent interactions are basically charge attraction or repulsion. And they can also involve interactions between not only charges, but partial charges. So we need to talk a little bit about that. The classic example of a charge-charge interaction is what I would call an ion pair. So one example of this is the attraction between positively charged sodium and negatively charged chloride in table salt. That's what's holding the table salt together. You learned about that in general chemistry, and somebody maybe told you that it was an ionic bond. In organic chemistry, we reserve the term bond for a covalent sharing of electrons. Instead of an ionic bond, we'll just call this a charge-charge interaction. If you've had any physics, you know where this comes from. You maybe have heard of Coulomb's law. This is the attraction between two charges is related to how big the magnitude of the charges and the distance between them. And we could write down an equation, but we don't need to. Qualitatively, that interaction is stronger when the charges are closer together. Of course, charge-charge interactions can also be repulsive, right? If you bring two like charges, they will repel each other. Another example of an ion pair in an organic molecule might be something like this tetramethylammonium cation. Cation means a positively charged anion, or positively charged ion. By the way, that is not pronounced cation, it is pronounced cat-ion. If you say cation, I will try to be respectful and not laugh at you, but I probably will giggle a little bit. So, and that's not nice. We shouldn't giggle at people that are just learning, but it just strikes me as funny. Well, I still remember when I was a undergrad student here and taking OChem, I was sitting in this room where they now have the tutorial lab, and I was listening to two students try to explain things to each other, and they were using cation instead of cation, and I giggled to myself then, which tells you how much I've grown in the past, 26 years or whatever. But all right, so an attraction between a cation and an anion. Anion means a negatively charged molecule. So this carboxylate can interact, the carboxylate anion can interact with the ammonium cation, and the two charges attract. And again, you don't pronounce that like onion. It's not anion, it's anion. There we go. Okay, so ion pairs are considered the strongest of the non-covalent interactions. Go ahead.
How do you represent the difference between the charge of an ion or a molecule and like the ownership of a specific atom?
So how do you distinguish between the charge overall on a molecule and the ownership of a specific atom? The formal charges in a molecule have to add up to the overall charge on the molecule. So when I put that positive formal charge on the nitrogen there and I don't show any other formal charges, that communicates to you that the overall charge on that ammonium ion is +1. But that's not your question.
No, like how do you want us to show the difference? Does that make sense? Like, because you were talking about formal charges and you have...
We're going to get there. So I think you're pointing out that I've said before that formal charge is just a bookkeeping way of counting electrons versus nuclei of atoms and coming up with the right answer. Just because I have the positive formal charge on the nitrogen doesn't necessarily mean the nitrogen's electron poor, and you have to use some electronegativity intuition to figure that out, and we're totally going there next. Yep. All right, ion pairs are considered, as I said, the strongest, but we need to put that in, I guess they're not called air quotes if I write them down. We need to put that in quotation marks because the real question with non-covalent interactions is strong relative to what? So, for example, what happens when you take table salt and you put it in water? It dissolves, right? And the ion pair breaks up. Now, if you just took table salt and tried to melt it to break up the ion pairs, you'd have to heat it up pretty high. I don't know what the melting point of NaCl is, but I think you can't do it on your stovetop. You need a much hotter oven than that. So what is it about water that allows those ion pairs to break up? It turns out you're not only breaking up the ion pair when something dissolves, but you're also replacing the ion pair with another kind of interaction, which we would call, I would call ion dipole. So an example of an ion dipole interaction, first we need to talk about what a dipole is. A dipole happens when a bond is polar. So if we look at water, oxygen is more electronegative than hydrogen. That tells you that the electrons in the OH sigma bond lean towards oxygen. that means that the oxygen is going to be relatively electron rich, and the hydrogens or the protons are going to be electron poor, right? So I will represent that with this lowercase Greek letter delta and a minus to indicate that even though the overall molecule itself is neutral, the oxygen has a partial negative charge on it. The electrons are leaning towards oxygen. The oxygen is electron rich. The hydrogens are electron poor. Lowercase Greek letter delta meaning a small increment of positive charge out on the hydrogens. Yeah?
So, something I've always been confused about is why is it partial? Like, what makes it kind of back and forth, partially charged?
So, what makes a partial charge versus a full charge? These ions here are not sharing electrons at all. Sodium and chloride are not sharing electrons at all. In fact, you would never draw a Lewis structure like that. The difference in electronegativity between sodium and chlorine is so strong that there's no point to sharing electrons. The chloride takes all of them, Cl minus, and then the sodium doesn't have the 2 electrons, Na plus. But we're imagining and at the other end of that sort of continuum, you have a full covalent bond, 2 hydrogens that are similar in electronegativity. Of course, they share the electrons evenly. But somewhere along the line, you have this space between fully ionic and totally evenly shared electrons covalent. What I'm telling you is the OH bond is still covalent, but the electrons spend a little bit more time on the oxygen side than they do on the hydrogen side. So overall, if you average it, the oxygen experiences more electrons than the hydrogen does. So that means the oxygen has a partial negative charge on it. Now, it's not a full negative charge. If it were a full negative charge, that would mean 2 of the electrons from that bond are just totally on the oxygen, which isn't true. Yeah. Yep, so this concept of when there's a difference in electronegativity between 2 atoms in a bond is called bond polarity. And bonds that have a significant difference, bonds that have a significant difference in electronegativity between the 2 atoms give rise to this bond polarity thing. So you need to know some things about electronegativity trends. For example, you probably learned in general chemistry that electronegativity increases left to right as you go across the periodic table. That is, nitrogen's more electronegative than carbon, oxygen's more electronegative than nitrogen, fluorine's more electronegative than oxygen. Similarly, electronegativity increases as you go up a column of the periodic table. Fluorine is way more electronegative than chlorine versus bromine and so on. Okay? And if you can remember those trends, it'll help you recognize polar bonds. Most of the things you're going to see in biochemistry that have polar bonds are going to be OH or NH bonds. Also CO and CN bonds. So if a bond is polar, if a molecule has polar bonds, well, let me back up just a little bit. It turns out that this non-uniform distribution of charge with a partial negative on the oxygen and 2 partial positives on the hydrogens, those are vector quantities, and they add together to make something called a dipole. A dipole is a distribution of charge along a line. Ions are point charges. Dipoles are lines. So what is the dipole line for water? It looks like this. We use an arrow for the negative end of the dipole and a cross for the positive end of the dipole. It's like a little plus sign that indicates this side of the molecule is electron poor, and this side of the molecule is electron rich. Now, What is an ion-dipole interaction? Let's look at it in the case of sodium and chloride getting dissolved. A sodium ion, which has a full positive charge, can interact with water molecules. But you tell me which portion of the water molecule is going to be pointed towards the sodium ion? Oxygen. Why? Because it has a partial negative charge. So the sodium ion in water has a shell, and I'm just showing you some of the water molecules. So people have done the math to figure out how many water molecules surround a sodium in solution. I'm not showing you the positive end of the dipole, just the negative end on the oxygens. When sodium chloride dissolves, we're going to replace ion-ion interactions with lots more ion-dipole interactions. Same thing with the chloride. What end of the water molecule should be pointing towards the chloride? Yeah, hydrogens, right? So we might draw that like this, all the hydrogens oriented towards the chloride. And so on. So this is why strength is always relative to what, right? An ion pair is strong relative to separating the two ions to get apart from each other to an infinite distance in a vacuum. But that ion pair interaction is not strong relative to being replaced by a ton of ion dipole interactions from water. Let that sink in for a minute. Questions about that? Go ahead. Yeah. An ion pair interaction is strong relative to taking the two ions and separating them to infinite distance in a vacuum, meaning surrounded by nothing. But it's not strong relative to having the two ions surrounded by water molecules and ion dipole interactions. Okay, so a lot of processes in biochemistry are related to these kinds of comparisons. Changes from one arrangement of atoms to another where the interactions between molecules change. And so you have to have a way of thinking about those rationally. There's a lot more we could say about the Gibbs free energy and enthalpy and entropy. Have you ever heard those words before? Ish. It was probably painful. We'll probably try to avoid it, but if you want to get into it, you can ask me. Go ahead.
I was going to ask if you're saying that ion dipole interactions are referable to ion pair interactions, or it just depends on what it is?
Okay. That question made me have to talk about entropy, enthalpy, and delta G. So I'm not going to do it too much, and you're not going to do any math. Just work with me. Gibbs free energy describes whether or not something is favorable. If Gibbs free energy is negative, that means it's favorable. If Gibbs free energy is positive, that means it's unfavorable. Delta means a change in Gibbs free energy for a process. So if delta G, if the change in free energy is negative, that means the process is downhill. If the change is positive, that means the process is uphill and unfavorable. So there are two parts to delta G. One is enthalpy. And you can think about enthalpy as being related to two things for a process: strength of bonds formed in a process, I'm meaning here covalent bonds formed, versus broken, or strength of non-covalent interactions formed versus broken. The other portion of delta G comes with a negative sign times temperature times delta S, and this is entropy, and entropy means disorder. And If entropy is positive, that means the system is more disordered, more unorganized. And if it is negative, that means more ordered and more organized. Okay? So to determine whether, for example, it's favorable to break apart an ion pair between sodium and chloride and replace it with ion dipole interactions, you got to consider two parts to this question. The first question is, are the interactions you form as strong as the interaction you broke? And if we're ballparking it here, I would say the ion pair interaction between two ions is strong, and an individual ion dipole interaction is weaker, but each sodium ion has many ion dipole interactions, and each chloro has many ion dipole interactions. So probably the strength of the interactions you form upon dissolving are a little bit stronger than the interactions that you broke. So probably enthalpy is negative or favorable there. Entropy. Think about in sodium chloride, all the sodiums are next to chlorides. It's a very ordered shape. Have you ever seen a model of what crystal salt looks like? Little dots for sodium and interspaced between little dots for chloride, all in this great cubic sort of lattice. That's very ordered. When you dissolve it in water, the order goes away, and each sodium ion is free to diffuse away from each chloride ion. So dissolving favors entropy, or entropy favors dissolving. Dissolving increases entropy, which makes delta G more favorable. So that's how I think about these kinds of things. We probably aren't going to push it to that level of understanding very often, but that's sort of how you think about non-covalent interactions. Okay, others? All right, I want to zoom in on a special kind of dipole-dipole interaction. It's called a hydrogen bond. This is kind of squares and rectangles. All squares are rectangles, but not all rectangles are squares. All hydrogen bonds involve dipoles, but not all dipoles involve hydrogen bonds. So what is a hydrogen bond? This is an interaction between the electron poor hydrogen in, say, a molecule that has a polar bond between oxygen and hydrogen. And I'm going to use a dotted line to indicate this interaction, and the electron-rich atom of another molecule. So in water, partial negatively charged oxygen on one water molecule interacts with the partial positively charged hydrogen of another molecule, and that's called a hydrogen bond. These can be pretty strong. And this is the reason why water is a liquid instead of being a gas at room temperature. Zooming back up, what do you know about the electronegativity of carbon relative to hydrogen? The difference is not that big, right? I don't actually know the numbers off the top of my head, but the difference for oxygen and hydrogen is quite big. The difference between carbon and hydrogen is minimal. So these bonds are less polar, meaning there are much weaker dipole-dipole interactions. In contrast, OH is much more polar. The OH bond is much more polar, which leads to stronger hydrogen bonding interactions. So water molecules are held more tightly to each other than methane molecules are. Yeah?
Doesn't the shape of methane, the shape of water also affect this?
Yeah, the shape matters too. It's not only bond polarity. So for example, you could ask, well, what if I make carbon bonded to 4 chlorines? Chlorine is much more electronegative than carbon, so you'd expect all of the chlorines to have delta minuses. However, I told you that bond dipoles are like vectors, and vectors can cancel each other out. So if you have all of these dipoles arranged to the corners of a tetrahedron, they all cancel each other out. And carbon tetrachloride is actually very nonpolar. So yeah, shape matters. It just so happens with water that water doesn't have a symmetrical distribution of hydrogens around it. It's got one side with an oxygen, one side with hydrogens. And that's the other thing that allows these dipoles to matter. Yeah?
So you said carbon's not involved in hydrogen bonding. Is it just nitrogen, oxygen, and chlorine, or which one?
Generally for hydrogen bonding, you're looking for HZ sigma bonds. And generally Z equals nitrogen and oxygen. We could include fluorine on the list. Fluorine's actually not found a lot in biology, so if we forget about it, it's not going to matter that much. Okay, hydrogen bonds are tremendously important. It's the reason that water is a liquid. Hydrogen bonds are also one of the reasons why water's density decreases when it freezes, which is really interesting. Ice floats, right? You all know this. That's actually really fortuitous for our survival on this planet. Maximum density of water is at about 4 degrees Celsius. That means that as water's temperature increases, it gets less dense and floats towards the surface of a body of water. As the temperature decreases to 4C, it gets more dense and goes towards the bottom. If it gets colder than that, density decreases again and it starts to float to the top. If that didn't happen, all our bodies of water would start to freeze from the bottom up and we'd have a lot less water to deal with. So one of the reasons that that's the case is if you've ever seen the structure of ice, it's an elaborate sort of chain of hydrogen bonds forming sort of 6-membered rings. I'm going to just give you an example of what this might look like in the form of a chair. So here I'm showing you an arrangement of 3 water molecules forming kind of a 6-membered ring. And you could imagine each oxygen having 2 lone pairs. Each of those lone pairs are going to be hydrogen bound to 2 other protons. You're seeing an example of that here, where the 2 lone pairs on that oxygen are hydrogen bonding to 2 other hydrogens. Well, what about this one? Well, I suppose it would be hydrogen bound to something here and then here. And you could imagine this extending in all possible directions where each oxygen is covalently bound to 2 hydrogens and hydrogen bound non-covalently to 2 other hydrogens. And this is where ice comes from. And that 6-membered ring shape is one of the reasons why ice crystals like snowflakes have sort of 6-fold symmetry, if you've ever seen a snowflake with that kind of shape. Anyway, so we owe hydrogen bonding to the fact that ice floats, which is really important for our survival. Okay, dipole-dipole interactions can occur between things that don't have hydrogen. An example of that might be this ketone. So in this ketone, you have a carbon that's less electronegative than oxygen. You would expect the oxygen to have a partial negative charge and the carbon to have a partial positive charge. And you might expect this dipole that we've drawn, you might expect multiple molecules of the ketone to orient themselves with this kind of arrangement such that the positive end of one dipole is next to the negative end of the other. These dipole-dipole interactions are weaker than hydrogen bonding, and the reason for that is hydrogen is small, the dipoles get closer together, dipoles approach each other more closely, if one of the atoms is hydrogen. And for dipole-dipole or hydrogen bonding interactions, these are highly dependent on distance. And because they involve partial charges, they are shorter range than ion pairs. So what I'm saying is just because of sterics, this carbon can't get very close to that oxygen, and so the interaction is not quite as strong. Okay. So we're gonna take a break here, but I'm gonna leave you with something to ponder over the break. We've got some non-potable industrial water here, which I'm not gonna drink, but I may spray all over myself. All right. Liquid at room temperature. And here we've got Crisco, also, let's see, pure vegetable oil. They said this was soybean oil, also a liquid at room temperature. But as you can see, they don't mix that well. And we want to understand why. Ooh, that was fun. I'll do that all day. You can see they form a layer between the two of them. They're not mixing. Now you know what holds water together, and that's hydrogen bonding. But if you know about triglycerides and you go look at the triglyceride structure, there's no electronegative bonds between there's no bonds between hydrogen and an electronegative atom in the triglyceride. The triglyceride is mostly CC and CH bonds. It's not very polar. Sometimes, at some point in the past, you may have learned the principle like dissolves like. So polar molecules like water dissolve other polar things. Non-polar molecules like triglycerides dissolve other non-polar things. But that's more of an observation than it is an explanation. And what we want to explain in our time together today is why the oil and the water are separating out. Okay? And just to prove that this is the case, I hope I'm not going to make a mess. I'm going to stand real close to these front row people in the splash zones. No. I'm just going to shake it up. Suppose I try really hard to mix those two together. Really hard to make and we're going to give it a few minutes to sit and see if it's able to separate out. All right, so go ahead and take a break, and we'll see whether we've truly dissolved the oil or not.